Have you ever thought about a circle that is stuck inside a parabola? Well, if not, today I'm going to share with you some of the very interesting properties of this kind of circle, such that it rests inside a parabola and is tangent to it at 2 points. For simplicity, we're going to use the parent parabola y equals x squared. This is so that the center of the circle will lie entirely on the y-axis. So here the y-coordinate of the center is k. Also, we call the radius of the circle r. And before we get into the rest of the video, one very important thing to note here: if we let one of the points of tangency be the ordered pair AB, the second point of tangency will be the ordered pair minus AB, the negative x-coordinate and the same y-coordinate. Why? Because remember that parabolas are symmetric over the vertical line that passes through the vertex, and the vertex of this parabola y equals x squared is 0, 0. So the line of symmetry of this parabola is going to be the y-axis. So basically, any point that shares one property on one side of this will have the same property on the other side of the parabola. So we just reflect this point AB over the y-axis to get the other point of tangency minus AB. This is a very important thing to note before we continue into the rest of this video, which is going to be in 3 parts. And first, we're going to examine the relation between the height of the center of the circle and its radius. In order to find where 2 curves intersect on a coordinate plane, we must solve a system of 2 equations. And it's no different here for the circle and the parabola. In order to find at exactly what ordered pair xy they intersect, we must solve their system in terms of the variables x and y. What I'm saying here is that k and r, the center of the circle and its radius, should not be treated as variables. They are not something we are solving for. They should be values that are known to us. And a second important thing to note here is that both of these points of tangency with the circle and the parabola share a y-coordinate. Look at this, both b over here and b over there, as I established in the beginning. That means that in the system, there only exists one solution to the equation for y. There only exists one solution for y here. And that means we should only know either the k or the r to be able to solve for y and find the rest of the information. And that makes us believe that there exists a relation between k and r. Now that we know that a relation exists, we can actually get to trying to solve the system in terms of y. And we can do this simply by substitution. Y is equal to x squared by our parabola equation, and x squared is equal to r squared minus this whole y minus k squared from our circle equation. So if we substitute the x squared from the circle in the parabola one, we get y is equal to r squared minus y minus k squared. Okay, and now we have an equation only in terms of y and the things that are known to us, the radius and the center of the circle. And we can continue with the algebra from here. Let's open up y minus k squared, expand it to get r squared minus y squared minus 2yk plus k squared. And now we just flip the signs around to get r squared minus y squared plus 2yk minus k squared. That is equal to y. So now let's make it a bit more of a standard form quadratic. Notice that this is just a quadratic in terms of y, because the highest degree of the y here is the square. So we move this over all to one side to get to 0. We get that y squared plus y minus 2yk. Remember, moving over minus 2yk. And also then minus r squared plus k squared equals to 0, because we moved everything over to one side. And we can make this even more standard by factoring out the y's. The y squared stays as it is, but from y we can also factor out 1 and minus 2k. Get y times 1 minus 2k. This is our y term. And also our constants k squared and r squared as this, k squared minus r squared is equal to 0. Notice this is just a quadratic in the form of ax squared plus bx plus c. Well, not x, but y. You get the idea. And as I said in the beginning of this, this equation for y only has one solution because the points of tangency share a y coordinate. That means the discriminant of this quadratic equation must be equal to 0. Recall that the discriminant of quadratic is b squared minus 4ac squared minus 4ac. That means that if we set this to 0, we will get our relation between k and r. Notice our b term is 1 minus 2k, so we write 1 minus 2k squared minus 4 times a, that's just 1, we don't need to multiply by 1, times c, which is k squared minus r squared. This is equal to 0 because there's only one solution for y. And there you go, that is our relation between k and r. We can obviously make it much simpler, but this is basically it. From there, just a bit of simplification. And this confirms that a relation between k and r exists. So let's quickly simplify it to make it a bit better to look at. We can expand the binomial 1 minus 4k plus 4k squared, I believe. Then we can distribute this to get 4k squared minus 4k squared plus 4r squared. That's equal to 0. And we can just remove these 4k squareds because there's positive and negative here. And we get, I believe that, 1 plus 4r squared. If we move over the negative 4k to get a positive 4k, and we can just divide everything by 4, probably, right? We get 1/4 plus r squared equals k. So k is equal to 1/4 plus r squared. And this is our relation between k and r, where k is the height of the center of the circle, its y-coordinate, and r is the radius of that circle. And this relation satisfies a circle which is tangent to a parent parabola at 2 points. Now we can move on to the next problem. We can now use the relation we found between the circle's center and its radius to derive an even cooler relation between its center and the y-coordinates of the points of tangency, just using a bit more algebra. Notice how that we define the points of tangency a, b. That means if we substitute in a and b into the x and y of both the parabola and the circle, they will both hold true because point AB is both on the parabola and on the circle. So because b is our y-coordinate, a is our x-coordinate, we get a nice pair of equations. B is equal to a squared from the parabola, and also from the circle, a squared plus y minus k, no, not y is b, plus b minus k squared is equal to r squared, as such. And now to find a relation between k and b, we can just try to get this equation right here with our circle into a form such there is only k and b found in there. First one is easy, a squared is equal to b, so we just substitute in there. And for r squared, we have now a relation between k and r. So r squared, that is just equal to k minus 1/4. So we get an equation b plus b minus k squared is equal to k minus 1/4, all in terms of k and b. But how will this get us anywhere? Notice something extremely neat. This is just a quadratic, but in terms of what? If we move everything over, we get this. B minus k squared plus b minus k, right? Moving over k here and the positive b, and also moving over the 1/4 equals to 0. This is a quadratic in terms of b minus k. Notice how b minus k is both the square term and also the middle term right here. And this will be easier to see if we have this b minus k equal to some variable t. And so we got a quadratic t squared plus t plus 1/4 equals 0. And if you memorized every single perfect square binomial that there is, then you know that this is just a perfect square binomial of t plus 1/2 quantity squared. If you don't believe me, you can easily verify it. That means t plus 1/2 quantity squared is equal to 0. That means there's only one solution for t, which is negative 1/2, which means that b minus k is equal to negative 1/2, or even better, k minus b is 1/2. Why even better? Because now we know that in any circle that is tangent at 2 points to a parent parabola, the difference between the y-coordinate of its center and the y-coordinate of the point of tangency will always be 1/2, which is very neat. And now knowing this relation and also that relation, we can probably answer the question, what is the smallest such circle that is tangent at 2 points to a parent parabola? When I'm asking for the smallest such circle, I'm actually asking for the smallest such radius of the circle that is tangent to a parent parabola at 2 points. So imagine you're shrinking its radius, it's going down and down, these points of tangency are zooming in closer and closer and closer to the origin. And will they actually converge at the origin at one point? The answer is yes. Eventually, these 2 points of tangency will meet at the origin as 1 point of tangency. Why? I can answer that as well, because notice how these 2 points of tangency, they have both a positive x-coordinate and a negative x-coordinate too. The x-coordinates are the same, just their signs are flipped. Their absolute value, though, is the same. And when there will be 1 point of tangency is when both the sign of the a-coordinate will be equal. And by relation b equals a squared, the only time when something squared has a single answer is when that square is equal to 0. So a squared must be equal to 0. By relation, b must also be equal to 0. That is one explanation, but there are probably several more. Also, it is just intuitive, I guess, for some of you. So eventually, these points will meet at the origin as a single point of tangency. And at that point, there will no longer be 2 points of tangency. And we can find the radius of that circle when it has such 1 point of tangency at the origin. That means b is going to be 0. That means k is going to equal 1/2. And by our relation, so yeah, if b equals 0, if a equals 0, then k will be 1/2 by relation of k minus b. And if we use the r squared equals k minus 1/4, we find that r is also equal to 1/2, which is pretty cool. They're both equivalent. And remember, at this point, there's only a single point of tangency. A single point of tangency. And that means our circle will no longer have 2 of them. So basically, the smallest such circle with 2 points of tangency is infinitesimally with a radius above 1/2. So if you add the smallest possible amount to the radius on 1/2, the single point of tangency will break and it will have 2 points of tangency. And that is the answer to the question. It is 1/2 plus, I guess, 1 over infinity. That is such a smallest circle. And what is even more interesting, actually, if you make the radius less than 1/2, what will happen? Well, by intuition, it should be 0 points of tangency. And it makes sense if you use these relations. When r is less than 1/2, that means k is also going to be less than 1/2 by this equation right here. When k is less than 1/2, then the value of b will have to be negative, right? Because it still has to hold k minus b equals 1/2. When b is negative, that means a squared must be equal to something negative, or a must be a complex number. You cannot have a real square that is equal to something negative. And therefore, on this real coordinate plane, there will be no points of intersection. And that is really it for today's video. I have linked a Desmos in the description to an animation of such a circle of the parabola, if you're interested to look at it more in detail. And that is it for today's video. Thank you for listening to me talk about a circle that is stuck inside a parabola. See you in the next one.